Thank you so much for coming to this talk. I'm Yamaya Bourdain. I work for Dedalian, and I'm President of Americas and Chief Commercial Officer. And I'm really excited to talk to you today about how AI will transform flight. And I'll talk a little bit more about how we use it so that pilots, operators can achieve what we call situational intelligence. So, introducing us, we are Dedalian. We are a company that is headquartered in Zurich, Switzerland, and we have about 150 folks at the company. We also have a site in Latvia and, of course, in the US, and we sit in Phoenix. We are a group of overall computer scientists, machine learning experts, algorithm developers, hardware developers, software developers, airframe developers, pilots. And we've come together so that we can bring AI to the airspace, but in a safe manner. So let's talk a little bit about this jumbo kind of buzzword of AI and the taxonomy of AI. What is artificial intelligence and what do we mean by it? Well, AI has now become just a marketing term to describe machines having the intelligence of humans. And when we talk about AGI, or artificial general intelligence, that is the point by which machines have either matched human intelligence or surpassed it. Machine learning is a subset of artificial intelligence, and it involves training algorithms so that they can learn from and make predictions or decisions based on data. Furthermore, neural networks, they're a specific type of machine learning algorithm that are inspired by the human brain. So they're inspired by the structure and the function of the human brain, and they are particularly effective when solving complex patterns, such as in image and in speech recognition. Furthermore, deep learning is the use of many layers of neural networks. And these are used to model and understand complex patterns in large data sets. So it's deep learning, and maybe I should talk a little bit more about convolutional. Let's go a little bit deeper there. Convolutional neural networks or convolutional learning. These are particularly effective for visual-based data, image processing, taking large data sets of images and making predictions based on that. So it is CNNs that Facebook uses, or Google Photos uses, or Apple uses in order to tell the difference between me and my mom, even though I'm the spitting image of her. And then, of course, lately, everybody's been talking about generative AI. Generative AI is, it trains massive amounts of text data and to understand and generate human language. And then within that, large language models, they produce new information, okay? So we all understand what AI is and all of the terms that people use in AI, right? But we still have to answer the question of why. Why would we want to use AI in these applications? And particularly, why do we want to use them in aerospace? Well, we believe that AI can be used to save lives, and that's how we employ it in aviation. I'll give some examples. AI can help us to know where we are. We can use visual-based navigation that is as precise, sometimes even more precise than GPS. And this could help us in future applications of urban air mobility, particularly in environments where GPS is not as reliable, in urban environments that are heavily crowded. AI can help us to know where we can fly. Well, today, of course, in airspace, people use ADS-B, right? Everyone who's flying has a transponder. But what about birds? What about hang gliders, paragliders, drones? Obstacles in the airspace that would not have transponders. AI can help us to identify that traffic in the airspace. And it can help us to understand where we can land. In this application, we can use AI to identify a runway. And we can go even deeper than this. First, we have to detect the runway, and we can provide guidance all the way down to a safe landing. But we can also detect whether the runway is clear or not. Can we land safely? Is there an obstacle there? That's how we use AI. And why would any of this matter if you cannot certify it? Of course. Well, Dedalian, our expertise is in certifiable machine learning. We only apply AI in places that otherwise what's available today is human intelligence. And we only apply AI where certification is required. So of course, we had to work with the regulatory authority in order to develop the first proposal for how to certify artificial intelligence. And so we co-published with the EASA a series of papers called CODAN, Concepts of Design Assurance for Neural Network, where we introduced the concept of learning assurance. For folks here who are aircraft developers, you know that you have to achieve hardware assurance or design assurance. You have to achieve software assurance. Well, if your application is a machine learning-based system, then you also should achieve learning assurance. And so we have created what some people call the W model in order to guide a process for handling the data, handling requirements, handling traceability, of course. And as most people usually say, these things aren't deterministic. We address determinism as well in this series. So we started out with CODAN in introducing the concept of learning assurance. We followed up with the EASA. We co-published a paper, CODAN 2, where we took the learning assurance model and we applied it to a real-world application, being traffic detection. We then followed up with a paper with the FAA in applying the learning assurance model to a runway detection application used in general aviation. And we provide what we call situational intelligence. See, our traditional tools, they can provide our sensors, our instruments, they can provide a pilot with situational awareness. And it's up to the human and human intelligence in order to create a picture, a semantic understanding of that environment, in order to understand whether or not I'm flying in a safe corridor, or if I have to make a maneuver, for instance, to avoid a collision or to avoid an obstacle. But situational intelligence does a bit more. It provides the machine with that capability that today humans are responsible for. It's not only the ability to understand my current state and my current environment and situation, but it's that ability to anticipate and react to potential threats. So let's give some examples of this. Oops. Will this play? Can I get AV to play this video? Uh-oh. It should have been embedded. All right, well, this video shows what it's supposed to show. It shows a bunch of different scenarios, and it focuses only on non-cooperative traffic, or any traffic for which a human pilot would be responsible for identifying, because this would not show up on your traffic display. So we can track birds, we can track drones, we can do that above and below horizon, and below horizon is a pretty difficult problem statement, and that's actually where the value in our core IP lies, because we have to guarantee performance in all scenarios, at least in VFR, daytime VFR for us. So unfortunately, you're not able to play that. But let's move on. Wire detection, another example today. Search and rescue pilots who fly helicopters. Today, they are responsible for looking out for transmission lines. And in many cases, you go up in the air, and if you're in an environment that's new to you, you don't see those. They are invisible to pilots. I've been up in the air with pilots. You can't see them. And they are a huge source of traffic collisions, of airborne collisions of pilots. Sometimes it's not actually that the pilot didn't see the wire. Sometimes it's that the pilot landed but forgot that the wire was there when he or she took off again. So we can use AI in order to identify those wires and augment the pilot capabilities so that the pilot could see these in the area. Landing. We show here that we can use artificial intelligence in order to detect landing strips and provide safe guidance all the way down to the ground. We can also do this for a vertical approach as well. Real-time landing site finder. Now, these two show similar but different capabilities. On the one hand, if I am, say, a helicopter operator or a helicopter pilot, I'd like to know where I can land. So say for instance, if I'm in a scenario where I lose engine power and I have to drop the collective and initiate an auto rotation, I have to do all that and find a safe place to land at the same time. What if the system could drop the collective already and identify a safe place and provide that pilot with somewhere that is flat and without obstructions? The second, on the left-hand side, it's slightly different though. How about if this emergency scenario happens when I'm on some very complex and dynamic mission, such as fire rescue? What if I am in an emergency situation and I initiate my auto rotation, I know where I'm going to land, and then suddenly a tree falls in the area that I plan to land? With artificial intelligence, we can update the landing site. We can provide an alert to the pilot that that no longer is safe. Now this is where you should land. Positioning. In urban air mobility, we're finding that GPS is not necessarily as reliable. And so having some ability to understand where I am, to navigate in these complex environments, in these congested environments, is critically important. We can use visual-based data. Effectively, we can operate like a human pilot who knows his or her environment very well because they fly that area quite often. The system takes over 300 points at a time. And even in snow, even when it's later in the day, even when the the environment has changed. We can still identify to a high precision where you are. And we don't drift laterally such as GPS does. And so we can hold a hover for as long as you would want, and we can also fly in a circle and end right where we began. And this is real. The first product that we are launching is called Pilot Eye. It is currently in the process of being certified to Design Assurance Level C. And we are bringing this to the market. It is a visual traffic detection system that hybridizes the visual-based data and the neural network-based data with ADS-B in order to provide a traffic display to pilots that plots both cooperative and non-cooperative traffic. So now a pilot would have the capability to see that there's some other hazards as well. And ultimately, it reminds the pilot, look up, there's something there. This system we've passed SOI 2, we're certifying with the FAA, we're concurrently validating with the EASA. And we go into SOI 2 next month, and we expect that it'll be launched and on the market at the end of next year. The last Pilot Eye was for fixed wing. This one is for helicopters. It does slightly the same thing, but with a slightly different HMI. In cases for helicopters, they tend to want to know and see a view of the world, either synthetically or real-time camera feed. And so we merge our data with a synthetic environment or with the raw camera feed and a thumbnail that provides the pilot that this is why we think that there's something there. In helicopters, this is really important because they often fly at altitudes where they have a much higher probability of interfacing with some airborne collisions or airborne obstructions. So finally, future versions of our system, they can fuse the visual sensor with LiDAR, with radar, with weather awareness, ADS-B, FLARM. And AI can be used to analyze multiple streams of real-time sensor data and yield a recommendation, not just be another piece of information that's going to crowd and take attention away from the pilot. So our HMI will present the pilot with information that's needed only when it's needed and nothing more. And this will reduce the workload of that pilot so that they can stay focused on the mission at hand. We want the machine to keep focused on the machine so that people can focus on people. Thank you. And it sounds like, I think Olivia's coming with the cue.
Ladies and gentlemen, please welcome Olivia J. Pinon Fisher, Principal Research Engineer, Georgia Institute of Technology, to the stage.
All right, good afternoon, everyone. This is my pleasure to facilitate this panel on the AI's application across the aviation system. So, as Yamaya mentioned, AI is really nothing new. AI has been around for 80 plus years. The reason that it's getting so much interest and attraction today is because we now have the compute power to take all the benefits out of it. So when we talk about AI, what do we really mean? We're really talking about discipline concerned not only with just understanding intelligence, but also building intelligent entities, meaning agents, machines that can compute how to effectively and safely act in a wide variety of contexts and environments that are novel to them. So as we're going to see through this panel, there's a number of applications which AI supports. AI is used across the air traffic management system to help optimize airspace utilization and flight routes. It usually does that by building on and leveraging huge amount of data, whether it's weather data, aircraft performance data, flight plans, air traffic flow, to help generate insights in real time. AI is also a key enabler to autonomy and the ability of autonomous aircraft to detect and respond to potential hazard in real time, allowing them to navigate complex airspace safely and reliably. AI in the cockpit, Yemaya touched on that quite a bit during our presentation. We're currently seeing an increase in the use of computer vision to help with visual traffic detection and visual landing guidance, for example. AI and ML algorithms are also widely used to take advantage of the huge amount of data that we're collecting from aircraft through a variety of sensors to help predict when parts, components, and systems are going to fail, leading the way to what we call predictive maintenance and condition-based maintenance, meaning that we can actually take steps before things break and guarantee that the airplanes are going to not sit on the ground for too long. And then finally, we're starting to see what we call AI-powered digital towers, which are using advanced sensors, high-definition cameras, and computer vision to help monitor air traffic remotely. Obviously, AI is not without challenges, and our panelists are going to touch on that quite a bit today. Can be anything from the difficulty of integrating AI into legacy systems, which usually going to require extensive customization and updates to our existing infrastructure, to the very hot topic of regulatory compliance and the need for certification of AI technologies. So with that, this is my immense pleasure to welcome our panelists to the stage. So I will introduce them all individually, and then they will have 5 minutes each to give their opening remarks as well. So our first speaker will be Mike Jones. Mike is currently the Director of Engineering Services at Systems Technology. At STI, he's responsible for the technical direction of aerospace programs. Prior to joining STI, Mike worked at the German Aerospace Center, where he was responsible for research programs on the variable stability helicopter, ACT-FHS. His background is in the field of man-machine interaction, including aspects concerning flight control, vehicle handling qualities, and assessment. He's associate editor for the Journal of American Helicopter Society, CEAS Aeronautical Journal, and AIAA Journal of Guidance, Control, and Dynamics. He's a recipient of the VFS François-Xavier Bagnoud Award, Outstanding Contributions to Vertical Flight Technology. At STI, he is leading development efforts for the AI-based adaptive learning products, including for pilot training applications. Our second speaker will be Luis Alvarez. Luis is an artificial intelligence research staff at the MIT Lincoln Laboratory in Lexington, Massachusetts, with a research background in AI for homeland protection and air traffic control. During his career, he has led a variety of programs with focus in implementing and evaluating autonomous aviation systems, deep reinforcement learning in decision support, and surveillance system. His current research portfolio includes application of machine learning in aircraft emergency landing, critical infrastructure inspection, and aircraft conflict management. Previously, Mr. Alvarez led the development of the decision-making logic with ACAS-X, a family of collision avoidance systems for crewed and uncrewed aircraft funded by the Federal Aviation Administration. Specifically, he led the development of the AI component of ACAS-XU, the small uncrewed aircraft variant, integrating ground-aware collision avoidance and introducing coordination between small uncrewed aircraft to avoid collision with crewed aircraft. This concluded with the publication of the RTCA Minimum Operational Performance Standard for Airborne Collision Avoidance System in 2022. Mr. Alvarez has a master's in aeronautics and astronautics from MIT, a bachelor's in aerospace engineering from the University of Florida, and a bachelor's in mechanical engineering from the University of Florida. He currently serves as co-chair for educational outreach for the AIAA Air Transportation System Technical Committee. Next speaker will be Mark Britton. Mark Britton is a member of the senior professional staff at Johns Hopkins University Applied Physics Lab in the asymmetric operations sector. Broadly, his research interests include decision-making under uncertainty, safe artificial intelligence, and reinforcement learning with application to air transportation systems. His early works applying AI to air traffic control have garnered international recognition and have inspired further research among a growing global community. Prior to joining APL, Dr. Brittain was a member of the technical staff at MIT Lincoln Laboratory. There, he led development of an AI testbed for advanced air mobility, focusing on various research areas such as AI for decentralized separation assurance in high-density advanced air mobility corridors and in flight conformance monitoring. He's an AIAA senior member and serves as a member for the IAA Air Transportation Technical Committee. Holds a PhD in aerospace engineering from the Iowa State University. Our last speaker will be Paul Schifferle. Paul Schifferle is the Vice President for Business Development for Carlspan Flight Research, leading efforts to position the company to respond to market trends and industry opportunities. Prior to his current position, Paul was the Vice President of Carlspan Flight Research, responsible for all aircraft modification to and flight tests conducted with Carlspan's fleet of 8 experimental aircraft. He was previously Senior Director of Engineering and Senior Director of Program. Paul started his career at Schweizer Aircraft Corporation, when he was responsible for the development, modification, and FAA certification of light helicopter. Paul is an AIAA Associate Fellow, FAA Designated Engineering Representative, and holds FAA Commercial Sailplane and Private Civil Engine Land Airplane pilot licenses. Paul is a graduate of the State University of New York in Buffalo, where he earns a BS in Aerospace Engineering and an MS in Mechanical Engineering. With that, we're going to give you guys an opportunity to ask questions to the panelists. And then if we can bring the QR code. And then before we give you an opportunity to ask your questions, we have prepared a number of questions for our panelists for them to take turn in answering. So the first one will be, we know that there's no shortage of opportunities to deploy AI, but because we can't, doesn't mean that we should. So can you please discuss what are the scenarios or the situations for which you think you should not, or we should not rely on AI, or why?
Should we go through the presentations and then?
Yeah, actually, that's a good
one.
Yeah.
Okay.
All right, Mike.
No, that's great. Thank you. Yeah, so it's really great to be here, and I was really happy to be invited to this panel with these great speakers next to me, and really talking about the AI applications through different areas of aerospace. So it's a privilege to be here, and thanks for the introduction, Olivia. It's great. I'm going to be talking today about some of the work that we're doing at STI, looking at the applications of AI to pilot training and future pilot training. And as STI, we're focused on building products and delivering services to support the pilot, to support the human. And we really believe that there's a strong benefit from some of these AI practices to support the human, not to replace the human, but to support them. And so what I'll do is I will, does that come there? So in the pilot training aspect, first we should consider, okay, what's the current status? And one thing that maybe is also pertinent to the other panelists here is about the use of data with aviation safety. And we need to reflect on what the current situation or the current status is with the use of data. There's numerous reasons why aviation is becoming safer and the commercial fatalities are decreasing. But in a report in 2018, the FAA credits this in terms of how it approaches the safety oversight in detecting, in looking at risks and identifying them using data. So getting ahead of the curve and sharing the data between the airlines and the FAA to ensure that we're operating safely. And this whole aspect of collaboration and safety culture, whereby we work together to improve the safety, but we don't use it as a kind of disciplinary action. We're rather using it as a way to detect these events occurring. This has really spurred on the safety that we see right now through pilot training and application. And one of the reasons that the airline started to introduce this data and use this data was the shift from accidents being occurred by system system safety to more towards, unfortunately, termed pilot error or loss of control. And as they saw that system reliability improved, in fact, the accidents were towards pilot error, and they need to mitigate against that. I think right now we're entering a time where the systems should be incredibly, or in the future, is incredibly reliable, and so that reliability increases. The role of the pilot will also reduce, and therefore we need to see, okay, what's the next step of this? And the next step, we believe, is using AI to support this data approach and support this data analysis. One thing about using AI in pilot training that we need to think about is pilot training is also, in the future, going to go through a large paradigm shift. The top left figure shows what you would traditionally expect today in terms of using a level D simulation device and also a full cockpit. In the future, we expect that there's going to be a new breed of devices and training devices to achieve pilot performance, to look at pilot training. And what's going to happen is these are going to become much more affordable, much more reliable and usable, and therefore we can start to look at training in new situations and for new cases. I don't know if you saw that yesterday, Loft Dynamics just achieved the approval to use a device for flight training in the US under FAA, and so that's the first VR device to be certified for flight training in the USA. And so the great thing about these devices is that they don't need the big space of the traditional devices, and so we can imagine the way that we approach pilot training is going to change, and that's where we see a case for using adaptive learning and AI. Why do we see that? Some of the points there are shown on the slide. We want to support the human operator. They're not going anywhere soon, and so we see there's a big potential to use AI to support that training and development. Imagining an instructor, a human instructor, can we capture elements of what they do and what they understand, and then use that for the pilot training? To do this and to employ these AI systems, something that we'll probably talk about today is facilitating trust. Okay, how do we trust these systems? That's obviously a big challenge, but we need to gather the data and start to use these. And we see pilot training as the amount of data we're collecting to continuous learning is going to be a big benefit here. And really realizing the potential of these capabilities. How can AI support us in training? Is it through cost? Is it through efficiency? Is it through safety? These are some of the things that we're investigating and looking at for future development. And so what we're doing at STI is looking at the adaptive training and initial steps in looking at adaptive learning using AI techniques, using reinforcement learning for this. And one of the areas that we're looking at closely is the emerging AAM eVTOL field. There's a number of things that make this a good demonstration for this. The eVTOL industry, if many of you know, is emerging at a time of pilot shortage, of change and cost efficiency. And so the training paradigm is going to shift for eVTOL. The way that the pilots operate with the machinery is going to change. These should have carefree handling, single pilot operations. And so there's a big need for new regulations and new training paradigms for this type of aircraft. As we go through this, what we're doing is we're training AI to understand, to work like an instructor and to support the pilot so that we can recognize the trends and support them with their decision making. Some of the benefits from this that we can think about is a reduction in training time. These eVTOL or AAM has very tight timelines for this pilot training. And they're expected to need 60,000 pilots in the next years if they're going to really achieve their targets. The dropout rate for training also doesn't trend with those. We have the dropout of only one in 7 pilots actually graduates right now from flight training school. And we're envisioning that we can all use AI here to help raise pilot entry skills as they go through the progression of the syllabus, and also then to support the instructor, not just support the instructor, but also baseline the instructor. And so we're working on these aspects, and we see a large chance to get AI to support some of these decision making for the data that we're using already. So that's what we do.
Good afternoon, everyone. Today I'll be talking a little bit about some of the work that we're doing at Lincoln Laboratory with artificial intelligence. Specifically, my focus is in-air risk mitigation from the aircraft either colliding with other airborne assets or avoiding a weather system and rerouting around it. We do a lot of work also with the navigation performance monitoring of the aircraft, measuring how much battery the aircraft has, and essentially providing the pilot or autopilot on board or pilot on the loop information about how to avoid a mid-air collision. One of the programs that we led was the Airborne Collision Avoidance X, funded by the FAA, TCAS program office, that used transponder information, ADSB information, onboard radar information to detect intruding aircraft and provide the system with advisories on climbing, turning left, or changing their speed to avoid a mid-air collision with other aircraft. This system has been tremendous. It used AI, specifically dynamic programming, and when compared to the gold standard that is TCAS, it actually increased safety by 20% in our global simulated sets, and it reduced the nuisance alerts by 65%. That not only provides better guidance to pilots and trust from the pilots that whenever the system is alerting, it does mean you need to actually follow the RA, but it can also prevent go-arounds when you're about to land at an airport and reduce the fuel that is used due to these nuisance alerts. In some of our work today in this conference, we presented a neural network-based system that monitors the health of the aircraft, figures the battery state of your aircraft, future hazards along your routes, and decides a new route that you should take to an alternative landing area. So some of the work that Yamaya was talking about, essentially taking you to that field, right? Saying this is an area that you possibly could land because there's a low population density, and then having that final stage system like Yamaya presented decide, yes, you can land here, right? It's all right to do so. Or essentially if the airport that you're going to, there's a weather system that goes on top of it for a few minutes and you're not gonna have the ability to land there, reroute you to an alternate site that would be safe for you. Imagine that when we use AAM and there's no pilot on board or one pilot, you're going to have to help the individuals make the decision faster in a high density environment. Some of the other work that we're doing is in over the horizon weather forecasting, where you don't have radar coverage, right? They have 60 nautical miles from the coast or 120 miles from the coast, they have radar coverage. But what do you do if you don't know what the weather is in the middle of the Atlantic coming to you? So we've done some work with convolutional neural networks, with satellite imagery, data from lightning strikes, where we can actually augment the radar picture of ATC and give them an idea of incoming weather systems that are going to be impacting the traffic flow in any of their sectors. And last, a little bit of a different taste is in counter UAS, right? In the sense that airports need to have counter UAS measures to avoid delays or collisions with their aircraft in the departure or arrival lanes. If you remember a few years ago, Gatwick Airport had a SUAS that was essentially harassing operations at Gatwick, and it actually shut down all operations in the area. Some of the work that we've done is essentially putting radars out at airports as well as camera systems to detect intruding SUAS that should not be there, and then linking it with our own blue UAS that essentially follow a chase mission where they keep the other SUAS in the middle of the field of view, report back to law enforcement where that SUAS is, and the hope is to essentially catch the individual or the location where this SUAS came from. This is the type of technologies that we're looking at Lincoln Laboratory, and we're making great strides with artificial intelligence. I think one of the things that AI is best at is figuring out wherever there's uncertainties in your environment, exploiting information that a human or a SME couldn't really think about how to link together, and using that to make a decision support decision.
Maya, next.
I don't have one.
If you want to make some additional remarks, no?
Yeah, I'm good.
All right. Good afternoon, everyone. It's great to see everyone here. Thank you for attending today's Forum 360. I hope you all had, a safe and smooth travel to Las Vegas, especially after we're coming off a pretty significant disruption to our air transportation system, with the recent CrowdStrike event that, led to thousands of flight cancellations. So, say what you will, Windows 95 is starting to look pretty appealing now, right? My name is Mark Britton. I've had the pleasure and privilege to work on a number of NSF, NASA, and FAA projects, primarily involved around artificial intelligence, specifically reinforcement learning, and how that can enhance real-time decision support for air traffic controllers and contingency planning. And really, as we look towards, leveraging this technology, we must need to understand, what does it mean when we take this technology and then move it to an operational state? So overall, when we think about, this graphic that we see here, we find ourselves at, an interesting point in air transportation history where there are these new entrants. We have, uncrewed traffic management, or UTM, for small UAS operations. We have urban air mobility that's revolving around our electric vertical takeoff and landing, or eVTOL aircraft. And this environment is moving into this increasingly autonomous space. But when we look at an environment like this, we need to ask ourselves the question of, as we move towards increasingly autonomous operations in these new entrants, how can we leverage that technology into our traditional air transportation system that really impacts, many of our lives on a yearly, monthly, or even daily basis? And it introduces a lot of challenges, so some of which Olivia spoke on earlier when we think about human-AI interaction, systems of systems. What does it look like when we think of individual platform-level AI, and what does that actually mean when we talk about integrating platform-level AI with NAS-level AI operations? How do they potentially interact with one another? Do they have compounding benefits, or do they actually induce conflicts or race conditions with one another? Overcoming these challenges, though, we can start to realize the benefits. In the context of air traffic control, in the near term, we can think about how we could use AI to reduce the cost or time for training new air traffic controllers. In the far term, we could imagine, what does it look like when we apply AI in the sense of, increasing the situational awareness for a recommendation system that can provide suggestive guidance to air traffic controllers that can also incorporate other objectives in terms of, maximizing fuel efficiency in addition to the, primary safety objectives. And through some of our recent research, we have found that these learning-enabled systems, when applied to the air traffic control problem, can scale to extremely high levels of air traffic, and also, minimize the number of, loss of separation events. And furthermore, we found that when you make these AI systems at various levels, scaling up to, higher levels of traffic management, aware of one another, you can have compounding benefits. So you can have a system that might be doing route planning or strategic deconfliction, and when you make that aware of a system that is doing air traffic control, for example, you can achieve extremely high throughput. You can reduce ground delay. You can maximize fuel efficiency while maintaining that high level of safety that we see in air transportation today. So when we think about evolving and addressing these complexities of air transportation in our system, as we look to strive for a more sustainable, more efficient air transportation of tomorrow, we still need to think about air transportation today. How can we modernize the NAS that we have now that just has an impact on our daily lives? So I'm really looking for the discussion with my fellow panelists, and I want to thank them for inviting me to talk today. So thank you very much.
Good afternoon. My name is Paul Schifferle from Calspan Flight Research. It's my pleasure to be here at AIAA Aviation to talk to you a little bit about more than 2 decades worth of autonomy testing in an airborne environment. I'm probably the one that's not like the other compared to my fellow panelists. I represent Calspan Flight Research, an organization that traces its lineage all the way back to World War II and the Curtiss-Wright Aircraft Company back in the 1940s. We operate a fleet of highly modified experimental aircraft. We've got 4 Learjet in-flight simulators. We've got a Gulfstream G3 that one of our customers affectionately calls the Swiss Army knife of airborne testbeds. We also maintain and support the X-62 Variable Stability In-Flight Simulator Test Aircraft, or VISTA, at the Air Force Test Pilot School, Edwards Air Force Base, California. If you Google search X-62A, you will find all sorts of good information regarding some artificial intelligence flight testing that was done not too long ago, becoming the first aircraft the first supersonic tactical aircraft to actually operate with an AI pilot. And we're certainly proud to be part of that program that transformed the aircraft, along with Lockheed Martin and the Air Force Test Pilot School, to make that aircraft the preeminent artificial intelligence, machine learning aircraft, certainly here in the United States, and I suspect in the world. So what do all these aircraft have in common? Well, they all have a programmable fly-by-wire flight control system that makes it easy for our customers to come and implement their autonomy. Meanwhile, the airframe is protected from exceeding any of the basic aircraft limits. So very simplistically, we provide the aerial sandbox and the adult supervision. You bring the toys, and we go fly. So let's talk about the components of autonomy test execution. So back in 2020, in the midst of COVID, these 2 Air Force officers were nice enough to put together this technical information handbook on how to test and evaluate autonomy in aerial platforms. And in this document, in which Calspan's mentioned several times by name, they talk about 4 components. The first of those components is an open system architecture. Make it easy to implement your autonomy and go fly. The second component is runtime assurance. Taken at the very top level, protect the airframe that you're going to be flying in. Number 3, use surrogate test platforms. You can test a lot of autonomy prior to the vehicle in which that autonomy is intended ultimately to fly. And last, be able to participate in live virtual constructive exercises. And LVC exercises are particularly important when you're talking about autonomy that involves multiple aircraft. So as we at Calspan looked at this document and read through it, we realized that honestly, for decades, we have had this capability. We've done this sort of testing. Our vernacular is not the same as what you see here on the screen. So what used to be the variable stability system has now become the experimentation platform for enhanced research and testing. I'm here to tell you that more than one adult beverage and with more than one Calspan person was required to come up with that acronym that I think more fully and accurately represents what we're actually doing with our aircraft today. It's not about variable stability for manned operations. It's about being able to test autonomy. So let's talk a little bit about how the expert system works and then ultimately what its benefits are. So we start with usually a early model Learjet, a Learjet with a mechanical flight control system, a reversible flight control system. The control inceptors in the cockpit are mechanically connected to the control surfaces. And effectively what we do is split the flight controls down the middle. The left side remains standard Learjet, and that's where our safety pilot operates the aircraft from. The right side becomes the programmable fly-by-wire side. So we install sensors, control surface actuators, fly-by-wire computer, pilot vehicle interface in the aircraft. Now at this stage, we've essentially got a highly augmented aircraft for manned operations, and historically that's what Calspan's been known for. Now, let's take it a few steps further to turn it into a UAV surrogate. So I'm going to use an example of some of the automated aerial refueling flight test work that we've done literally over the last couple of decades and actually continued even to do this today. So here you see the Learjet, most notably with an aerial refueling probe. It's the only Learjet that you'll find, the only business jet in the history of aviation to actually connect itself to another aircraft back in the day. But if you look closely, you'll see a bunch of apertures on the nose. We're really good at taking a perfectly good airplane and making it a little bit ugly. So behind all these apertures are sensors that are all part of the automated aerial refueling system. And finally, we've got to add some control. So, some sort of autonomy, some sort of artificial intelligence that's going to control all this. So when we put this all together, we now have an aerial refueling surrogate receiver. And this picture shows one of our operations from not too long ago. The picture's taken from the left side of our Learjet. You see the probe in the foreground. You see us approaching the lit basket or drogue that's on the end of a hose that's connected to an aerial refueling store that's attached to the bottom of our Gulfstream G3. We've actually kind of formulated and developed our own little CalSpan aerial refueling ecosystem, if you will. So we're doing a lot of development, a lot of autonomy work in that regard, and that's just one example. Okay, so that's kind of how the system works. So what are the benefits? Well, first, if it's important, we can actually replicate the flight dynamics of the aircraft being simulated. You provide us with the stability and control model, we'll implement it in the fly-by-wire computer, and when you push the button, it's not flying like a Learjet anymore, it's flying like the aircraft we're trying to simulate. Second, these aircraft can actually be modified with the sensors and mission systems that would ultimately go on the end vehicle, and those can be integrated with the rest of the control system. Third, you've got access to a full authority programmable fly-by-wire flight control system. This is not operating through the autopilot. You have access to the complete 100% controlled deflection of every control effector on this aircraft through high bandwidth actuators. Fourth, you can safely and efficiently conduct research, development, test, and evaluation early in development. You can get a look ahead at what your system is going to perform like when it gets into the final vehicle. And all this can be done because we've got a CalSpan safety pilot on board if the autonomy or if the system under test decides it's going to do something that you really didn't expect. Okay, let me move on and talk for a few minutes about the latest aircraft in our fleet of in-flight simulators. This is Lear 5. This is a modified Lear 31 with the Expert system. This is good timing for this talk because the aircraft conducted its first post-modification sortie back on June 28th, so just a little over 5 weeks ago. And if you could play the gratuitous 15-second video, I'd appreciate it. We got audio, that's good. There we go. Okay, thank you. All right, so let me talk a little bit about its capabilities and how it compares to previous versions. So it's got the open system architecture. It's a little more open than our previous versions. It's also got runtime assurance, and that's worth a few minutes of discussion. So our runtime assurance takes the form of our safety trip system. So in the cockpit, we've got a host of buttons that the safety pilot can push to disengage the system. There's a button on the yoke, there's a button on the throttle, there's a button on the center console, and believe it or not, there's actually a button on the glare shield for the pilot to headbutt to disengage the system. CalSpan lore has it that that button has only been used in anger one time when the pilot's hands were full as he was trying to recover from a situation. Additionally, we've got an automatic safety trip system that continuously monitors aircraft states, combinations of aircraft states, and will automatically disengage the system if we get to a limit. My favorite safety trip is the top tail rolling moment. Many of you perhaps know that if you combine rudder deflection and angle of side slip, you can damage the vertical stabilizer on an aircraft to the point where you can take it off the aircraft. So we have a safety trip. We measure angle of side slip, we measure rudder deflection, we calculate dynamic pressure, and there is a limit that grows and shrinks with dynamic pressure. Curiously enough, in the year 2024, most of our automatic safety trip system actually resides in the analog electrical world. We do that because if there is power on the aircraft is protected. Okay, sensors and mission systems. Now, we've done some of this in the past, but this aircraft brings a little more to the table. We've actually installed provisions for wing-mounted pylons that'll carry external stores and mission systems. We've got our nose mount provisions. What you see here is one of 8 different nose cones that we have for the Learjet with a variety of apertures that can accommodate electro-optical, infrared, RF, radar, SATCOM, lasers, LiDAR. We've flown a whole variety of these systems. Data links. So we can, of course, go ground to air. We can go air to air. We can also go space to air. Now, space to air could be simple SATCOM, but it also could be high bandwidth optical communication from space. If you've paid attention to the media, you might know that the Space Development Agency has their first tranche of high bandwidth optical terminals in orbit, which absolutely phenomenal in terms of the bandwidth of information that can be passed. Cross-domain solutions. So a lot of data flowing through the aircraft. We've got aircraft state data, we've got sensor data, we've got mission system data. Much of that data is unclassified, but some of it is classified, and it's classified at different levels. So cross-domain solutions allow us to parse that data and make sure that we don't contaminate, most importantly from our standpoint, the aircraft, but make sure the data goes where it needs to go. And last, test bed in a box. Essentially, it is a expert digital twin. Now, ask 10 engineers to define digital twin, and I think you'll get 10 different answers. Effectively, we provide a computer with the expert system embedded on it, and we provide that to our customer. Our customer then, in his own spaces, with his own people, with his own tools, can do a lot of the integration. Essentially, our customer plays a home game, right, in sports parlance. Everybody wants to play a home game as opposed to an away game. So they get the system working, they get it integrated, and then they come to CalSpan. We do a quick installation, we do a quick ground check, and then we're off and flying. It tends to be very, very efficient. Okay? So that's Lear 5. Lear 6 is in the offing. We expect to have another Lear 31 in the hangar in about 2 months, and then we'll get to work on modifying that aircraft and add that to our stable. So thank you very much.
Thank you. Thank you all, and for your exciting work and the capabilities that you're developing. I would like to offer the opportunity to the audience to ask their question. If you can scan the QR code here so that we can get to your question eventually. So as you do this, we have a number of questions that we wanted to ask our panelists. The first one is, as we mentioned, right, there's no shortage of opportunities to deploy AI, but because we can doesn't mean that we should. So wanted to ask each of our panelists, what are the scenarios, the situation for which you think that we should not rely on AI, and why?
I guess I can start on that. It's a difficult question because I don't want to pour water on anybody's research here, right? But I mean, I think I'm an aerospace engineer, and modeling and simulation is one of the topics that I work on a lot. And I think what we see in modeling and simulation right now is employing AI to come up with non-physics-based models. Which is great. We can then leverage all the data that we're collecting, and we can produce models that are very, very accurate, and use those for some of the applications we've talked about today in the intro slides. But then we have to start to consider what happens if you extrapolate beyond that. And I think that's a key for a lot of the technologies is to make sure we understand what we've trained the models for, and understand, okay, when we use this for certification training or so, how is that extrapolation going to materialize? Because that model that you're developing is not at the end of the tool chain. It's not the control system or something at the end. It's really in the middle. And so as we employ these AI techniques, I think it's very important that we think twice before we apply these to to situations where you extrapolate the data to get failure conditions, those sorts of things. That's what I'd say.
So I think that in any part of the airframe control, I don't think we should use AI in transport category operations, part 121. I say that because, again, AI should do one of three things: enhance safety, increase capacity, or reduce cost. And today, in Part 121, transport category airspace, it's extremely safe. When we come to using AI in order to do vehicle control, the operations are about as safe as you can possibly get, and they're not broken. Of course, there are other ways from an optimization perspective, from an operations perspective, and running a business like scheduling that we can, but from controlling the vehicles, I don't think we need to use AI in those operations.
Yeah, it's getting harder and harder as we go on in the panel, right?
Sorry.
There's so many good points. But I have to agree with my fellow panelists. When we have other methods that you can use, right, like path planning methods that guarantee some level of safety, are more explainable, can handle some level of uncertainty in the environment, you really have to make the case as to why you use AI. And I know that a lot of us use AI because that's what you're getting funding to use, right? You're getting a directive from someone higher up to say, well, what is this AI ML thing? I would like it in my contract. I would like it in my presentations. But you really have to think about what is that you're gaining by using AI. You lose a lot of explainability. It becomes incredibly hard to certify some of these black box systems unless you have some runtime assurance around it. And then the question might come up, if I'm using a runtime assurance system to map my output of my neural network to some controls that are represented through model predictive control, why do I even use the AI part? Why not use model predictive control? So I think you really have to think hard of when you're using AI and what are you trying to approximate through this black box system.
Yeah, so there's two different points I don't want to bring up here, maybe two different application areas. The first that I'll touch on, I introduced the air traffic control problem. I think air traffic control today is very safe. I don't think there's any reason that we need to just throw AI to, replace some air traffic controller because we have such a high standard of safety today. Now, that being said, I think that AI could be used in that domain, as I mentioned earlier, in terms of reducing the cost or training time of new controllers or providing enhanced situational awareness to reduce the cognitive workload of air traffic controllers. But for a system that we already have such a high level of safety, there's no reason that we should just throw in and try to replace a human. The second area that I think that we should not use AI is when we start thinking about decisions that are very ethical and how they're going to be made. So I think, my colleague Luis here was showing the UAM environment in terms of contingency planning. When we think about, would we really want an AI system to determine, an emergency landing zone just on the fly? I think it's one thing when you have a system that has pre-canned locations that have been, vetted beforehand, but really on the fly, computer vision landing. I don't want to be the one that's trying to answer questions of why this UAM vehicle landed at an elementary school, for example, right? So I think when we have situations like this, there's areas that we can pre-compute some of these locations. We could solve those using, some optimal control. We don't need to use AI in these decisions unless we really are advancing AI in terms of understanding the ethical side as well. So.
Okay, I'll take this a little bit further with regard to the ethics. I think any time human life is in the balance, I think there needs to be a human on the loop. Obviously, a lot of the things that we do at CalSpan have a defense-related theme. And we've all heard about swarming UAVs and so on and so forth. And I think there absolutely needs to be a human on the loop if we're going to be using vehicles in conflict.
So to kind of jump on a little bit to what you just said, there's a lot of when we bring up AI, we bring the question of trust and acceptance. Yes. So for the specific applications that you are all talking about and working on, what do you see as the main barriers to acceptance of the use of AI, and how can we best address them?
Okay, yeah, I'll start. So I think from our perspective in the testing that we've done to date, in some of the testing that we've been associated with, there is the assumption of perfect aircraft state knowledge, right? And I think we need to get beyond that. We need to add more real life sensors. Example I can use, you may be familiar with the DARPA Alpha Dogfight trials. It was a program in which 8 artificial intelligence providers went head-to-head in a simulated dogfight. It was kind of like the NFL playoffs. You know, you got 1 versus 8, 2 versus 7. Ultimately, there was a winner. The winner went head-to-head against a real Air Force fighter pilot in a ground-based simulation. The poor Air Force fighter pilot got thwacked, right? It was 5-0. It wasn't even close. I got to be honest, I was one of the guys running around our hangar, nerds 5, fighter pilot 0, right? And to which my fighter pilot colleagues did 2 things. First of all, they gave me the hairy eyeball. And second, their comment to a person was, if you could plug an Ethernet cable into the back of my cranium and I knew exactly what the other guy was doing, I'd be a whole lot better too. So this assumption of perfect state knowledge, while a good starting point, I think we need to add more and more realism into what we're doing.
I think building off of what Paul mentioned, there's some things that stood out to me and what you said, which is, high fidelity modeling and simulation environments such that we can actually enable this type of test and evaluation, and then having that human in the loop component as part of that simulation to actually build the trust in the system. One thing that we've seen in the air traffic control space is that, there's a lot of pushback if they're not understanding what's actually going on in the simulation environment, but enabling an environment where they are able to interact, they're able to learn and understand what that system is doing, I think is working towards overcoming the barriers in terms of adopting these systems in practice.
Yeah, I mean, there's trust and then there's trustworthiness, right? So in some of the contingency management work that we've been doing where we have to reroute the aircraft on an alternate site, I often have to remind my colleagues that the AI is not aware of everything. There's multiple layers of safety in aviation. You can't assume that it is going to know everything that a pilot would know if it can communicate with ATC. It can know about what is going on at that airport. Is there an aircraft in that runway? Why do I need to go to this route? There's a lot of layers of safety in aviation that I think you need to understand actually keeps us safe. So an AI system, even when an operator is interacting with it, you need to train the operator to know what are the bounds that the system should be trusted with. What was it meant for? What was its objective? And when can it go wrong? So that you don't have the personification of this AI that sometimes happens with like ChatGPT, Siri, or Alexa, where we are very quick to think that we're interacting with a human being that has the same state of mind as us. But it is an optimization problem. So it is trying to solve multiple objectives, and that's all.
I think we often, and I see this often where we equate AI to autonomy and autonomy to AI, so we use them interchangeably. That's one. But the second thing is we assume that AI has controls. And when we make that assumption, I think we do limit ourselves significantly in its ability to be useful into the airspace. But there are ways that you can use it. As I demonstrated today, in each one of those examples that I showed, each one was a pilot augmentation or a pilot alert and nothing more. And of course, I could further develop it such that it could provide a resolution advisory to the pilot and the pilot can make a decision. I could provide it as an input into a very classical system, right? Any autopilot does not need artificial intelligence enhancement. Any flight management system doesn't necessarily need artificial intelligence enhancement. It could take an input from, say, a perception system that comes from AI. And so there are many applications, there are operations where these are necessary. Again, when we introduce our technology, we're starting with helicopter operations. Why? Because general aviation has a long way to go in order to reach the safety levels that are enjoyed by transport category. And in more specifically within general aviation, helicopter operations. They say that statistically, helicopter operations are as safe or unsafe as riding a motorcycle. That's because when I have to go and do a search and rescue operation, there is no other option, right? I'm necessarily not expected to come back alive. I'm going into environments that are extremely unsafe. And so in those type of operations, when they look at our systems, they're like, get them to me as soon as possible because I have no other option. My other option, if I make a mistake in this environment, is I die. And my rescue operator, my hoist operator, and the patient all die. And so for getting them to market, I think if we target environments where we truly make a difference, and we can provide the technology in a way that we make a difference and we enhance the safety of their operations by enhancing their situational awareness or situational intelligence, then we could see this technology next year, right? As long as we don't assume that we're going to take over the controls.
Yeah, those are all great points from the panelists, and I think that one of the barriers to acceptance or things that we have to think about is obviously we're all passionate about the use cases and applications that we're putting forward here, but it's really to convince and to understand the benefit for the eventual stakeholder, like the search and rescue, like the pilot, like the air traffic controller. Like how do we show the benefits that we see to them and give them the trust? I think one of the things that we see, particularly when dealing with pilots or talking with pilots, you get one chance, right? And if that AI system and catch-all AI system, it does something that the pilot didn't agree with or did something that was potentially unsafe, that's it, it's over. They're always going to cite that and they're always going to remember that. And so I think that's one thing that we really have to think about is how do we show the benefits for traditional aviation right now, like air transport? We've had many years to perfect the system that we're running now, using data, using training, those aspects. So how do we now take AI and ensure that we can safely integrate that and also to show the benefits that we all clearly so much see in it? So I think that's one.
Oh, thank you all very much for your answers. To continue a little bit on that thread, one question that was asked from the audience is, who is legally responsible if an AI-informed pilot decision goes wrong? Is this the pilot? Is this the sensor manufacturer? Is this a software developer? Is this the airframer? It's not a loaded question at all.
Well, I would say that there is always an operator, right? There has to be someone who is responsible for pushing the button. And that person who's responsible for pushing the button, that person is providing their trust in that system, right? And so this is just like if I get a new employee who works for me. When I start training that employee, they're going to slowly increase their capabilities, and I'm going to slowly decrease how much I'm monitoring that employee. Now, if regular operations, the employee is going to get better and better and better until I trust that employee, and I'm okay. I stop overlooking that employee. But what if I give them the same task in a new environment? Now I have to start looking again, and now I have to keep paying attention. Mm-hmm. So these kind of systems work in that same way. Ultimately, as the manager of that task or that operation or whoever it is that needs to achieve that goal, I'm putting my name, my badge, and my trust in that system.
Ultimately, though, I think the developer of the system has to provide proper instructions of what are the domain that the system will work well in, right? Mm-hmm. So, I mean, look at some of the recent events with certain manufacturers. They didn't provide enough information to the pilots, or they didn't make a big deal about the training, right? So I believe that the AI roadmap from the FAA just got published a little while ago, and they talk a lot about responsibility and distributing responsibility both to the developers, the operators, like Amaya is saying, as well as any individual involved, right? Distributing that responsibility and seeing where did it actually fail. We're always going to have NTSB looking at reports of why something crashed, right? And they're always going to try to figure out who is liable for this. I often get nervous when I do sign some paperwork that uses AI to say, okay, where's this going? Because I wouldn't want anything that I'm actually developing to put someone at harm. And then do you come back for the intern who wrote that line of code, or who do you go to? That's an interesting problem.
Yeah, I mean, I definitely agree with Luis here in terms of like understanding the distribution of like the, responsibility. I mean, it's one thing for the operator. If we have a fully autonomous system where it's just like operating, all the time, then I feel like it definitely falls back to, the actual development team itself in terms of like who was actually writing that code. And we're starting to really understand and ask these questions, right, in the ground transportation space. So I think there's been a lot of instances in understanding, who has the actual responsibility when some of these events occur. So.
Yeah, I think, we think about how an aircraft is certified, right? There is a certification basis, right, that gets negotiated with the FAA, and then it's your job, say as a manufacturer, to prove that your vehicle, meets those requirements, right? So that is a loaded question. There's a lot of aspects to that, right?
Yeah, I think the answer to that question is it depends, right? I think it really depends. Like, is this a safety critical system? Is the pilot monitoring the system? Is it an advisory thing to the pilot? It really depends where the cert level is.
Are they operating it outside of the AFM? Because
Exactly.
every time I certify a system, I got to provide an AFM and tell my pilots when you can use it and when you cannot use it. Right? And anywhere I say that you can use it, that is what I have guaranteed the performance metrics of that system for.
Right.
I mean, aviation is held to a high standard of safety, right? We talk about human factors, and people fight over the color of symbols on displays because they mean things, right? Whereas in the ground transportation systems, it's the Wild West. I think the public is more sensitive to anything going wrong with any kind of aviation-related technology than they are to any ground transportation technology. If not, you wouldn't drive anywhere because there are a lot more accidents annually in ground transportation than there ever has been in air transportation. So that's something to think about.
So kind of stay on that topic of certification, verification, validation. Can you comment on how software verification and validation is done for any type of AI technology in the cockpit?
How software?
Verification and validation is done.
Yeah. So I can't go into deep detail here, but our company, we're currently in this process. We're certifying what the EASA has stated publicly they think will be the first system, machine learning based system to be certified. The FAA has publicly stated that they have 3 companies globally that are in the process of certifying a machine learning based system. We know that to be us. X-Wing, we don't know exactly what's going to happen with X-Wings now that they're no longer working on the 208, and they've been integrated with Joby Aviation, so we don't know what that STC is going to look like going forward, if they'll move forward with it. And then the third is Collins Aerospace. Of those 3, with the FAA, 2 of those are high dimensionality, traditional machine learning, convolutional neural network applications, with one of them not being that. It's really low dimensional. It's not what we consider today an AI application. So I'll give an example for us. We are taking a system that uses neural networks to scan the sky at all times. And today, pilots have access to a traffic display. The certified traffic displays go on the cockpit. they take in transponder data from ADS-B, and they plop all that data on a global map. Pilots have a non-certifiable option as well, and that option is a software called ForeFlight or Sky Deeming. They are basically flight planning apps, but they're not certified. And funny enough, in general aviation, pilots use those a lot. They use the uncertified, they use their phone or tablet during flight. For the traffic detection example, for validation and verification, well, the value proposition for us is non-cooperative traffic. So that being drones, birds, hot air balloons, hang gliders, paragliders, things that don't carry transponders. Birds being one of the hardest because obviously they can't tell you that I'm here, and they can't tell you where they're going. They can't tell you what their trajectory is, right? So we have to guarantee that we can track birds and we can put them on a plot. We will always be able to detect them. Well, what we can do for that, of course, when we collect data, we can't just go up in the air and look for birds and fly and chase birds. One, it's actually illegal because it's very, very dangerous. What we can do, though, is we do a lot of coordinated flights within our company, and we also fly a lot and build many, many, many flight hours in congested airspace. We, including with non-cooperative traffic. And then what we do in order to verify is that we have millions of data points. And actually from those, we take from like each data point, we can spin off at least 2 simulated data points. And we do our validation verification based on known data where I do have ADS-B available to me. And so if I can show to a very, very, very high number and high level that I track separately. So of course, my data for my modeling is completely separate from my test data. And I never use my test data in order to, of course, over model. So I keep those things separate. And if we produce enough data points that are verifiable based on ADS-B, and we can actually get that, we have been doing that for years, we've been collecting this data since 2016, then we use that in order to prove that we can do that for non-cooperative as well. And we have to also show that both above the horizon and below the horizon. Most people in our application of how we're using, they expect that, look, all I have to do is write an algorithm for non-blue sky. Yeah, you know what, that's actually true. But then when you go below horizon and you have solar panels behind you, under you, and you have people on the beach under you, and you have birds under you, it is a completely different story. And so we can use the known data points in order to prove that we can do this in non-cooperative examples as well.
Thank you.
Yeah, maybe one thing that would build off of that is, when we think about like certification and validation, verification, it's going to be very dependent on what the specific application is, right? This is something that we've already talked about. Is it a safety critical system? Is it something that's just, putting a little situational awareness, like this is what altitude you might want to navigate to reduce turbulence, right? In each project or aspect of how we integrate AI, into an aircraft is going to have its own set of verification and validation in order to actually go through the certification process. There's no, one size fit all, approach, and that's something that I think is highlighted in this recent FAA certification roadmap, is that looking at this kind of bottom-up approach where it is at like an individual project to work, with your CAA in terms of understanding what is the type of studies that need to be done in order to have that confidence in the system. I think this is something that Luis can speak to in terms of collision avoidance system when you're working with a safety critical application, in terms of how important it is to have community involvement, in order to make that case towards certification.
Yeah, definitely. I mean, we saw this in ACAS-X, which is not as high dimensional of a system as like a CNN, right? That CNN has even if it's a 480 by 480 image coming in, that's a lot of data coming into your system. And those pixel values can differ 0 to 255. So that's a lot of different permutations that you can have in your data, right? And we've seen also poisoning of the data to essentially get your neural network to think something else. But in ACAS-X, in a low dimensional input state space, we really only had 12 dimensions overall. We had to do over a decade of working with RTCA, EASA, ICAO, all of these organizations, showing them step by step, like Jemiah said. We have data. It's called encounter models. We have recorded data from flights. We created Bayesian networks that would model trajectories, and we can query and create simulated flights from those Bayesian networks. Even that by itself, proving that we could do that, was a step. Then going and saying, okay, well, we can use that data now to start training our system. Well, you don't want to overtune, like Jemiah said. You have to hold your data separately. There's test data, there's training data, there's evaluation data. And even after that, we had to do multiple flight tests where we actually tried to get RAs from our test aircraft. We had 10 aircraft operating over the NAS with experimental licenses where they had a TCAS box and an ACAS box at the same time, and they were comparing. Even after all of that is done, for ACAS-X, we have a monitoring system where there's actually a way, like now in TCAS, where every time there's an RA, we at Lincoln Laboratory actually get that data and we can analyze why did that RA happen? Was it suitable for that to happen? A system like that is still going to be available for ACAS-X, and there's continuous monitoring. And there'll be, I guess, even further work, right, for all these AI systems. When you update the system, you need to make sure that the system hasn't forgotten a previous objective, right? So if you're introducing now, hey, there's this new data type, there's this new entrant, they behave like this, you better make sure they don't forget how commercial aviation behaves. So you need to be always testing everything you tested before and more every time you update your system.
All right. Thank you very much. Another question from our audience was, what are the current and future risks you see when deploying AI to UAVs, especially with the emergence of unmanned air taxis and drone delivery services?
What was the first part of that?
What are the current and future risks you see when deploying AI to UAVs, especially with the emergence of unmanned air taxis and drone delivery services?
I mean, I've worked a lot with universities doing AI implementations into UAVs. I have a fleet of about 35 UAVs where we actually test out some of these systems. Something that's overlooked when you're designing an AI system is that you're living in a simulated world. And the data that you have access to, like we talked about with the ACE program, right? You don't have access to some of that data in the real world. And I have to constantly remind the students that I work with that you don't know that sensor measurement 1 kilometer from you. How are you going to get it? And they say, oh, there's some sensor out there that will give it to you. It's like, no, that doesn't exist. Also, you have to think about in the systems, the quality of the data coming in and the rates at which it comes in is very different. So this sim to real gap is a real gap that you need to look into. And I think we need to slowly, incrementally approach UAVs using AI systems, especially in urban environments. You saw early UAV operations where I believe they landed on top of a kindergarten. They dropped some syringes. You don't want that every day, right? We don't want to lose the trust of the public when they're looking up at the sky and they're seeing these UAVs.
So on the topic of data, obviously, we're dealing with vast amount of data. There's always the question of IP, privacy, and cybersecurity. So one question I was asked is, given the sensitivity of aviation data, what measures are being taken to ensure data privacy and security when implementing AI solutions?
I think that really depends on what the application is. Especially if you have to certify a system, right? From a safety perspective, you always, you start with your FHA, for instance. you also, for certified systems, you have to go through cybersecurity. I can't. Is it 365, or 362 or something, or 382? There's a standard, RTCA standard, for handling the cybersecurity kind of problems. And funny enough, sometimes the security measures are in direct conflict with the safety measures. And so if something, you might have something implemented in order to mitigate a security risk, that same thing might be impacting negatively the safety. And so kind of running through the entire process all at once is really important. But I do think that there is a decent amount of guidance that's available. Now, for data protection and data security, I'm not exactly, again, I think it's based on the application. For us, we are at such relatively high altitudes that, we don't see faces or anything. I mean, years ago when we took our system to the beach for the first time, it was picking up a bunch of bikinis, right? And we didn't realize, right? So we fly everywhere. We fly throughout the United States. We fly all throughout Europe because we want to be as many backgrounds as possible. But, we weren't seeing faces because we just weren't that, our systems, our cameras are not that resolved. But they are high resolution. We have 12 megapixel cameras. So I'm not certain exactly that for our applications at the moment that we see those problems.
I mean, it becomes an identify, track, and detect problem, right? So how high will you fly? What kind of data are you having? I think Google stumbled upon this when they had their ground transportation system, right? Taking ground images and telling you the street view of how things look like. Then they had to blur out license plates, people's names of businesses, and they actually had to open up a querying system where you can actually file a complaint and say, I would like this part of the image to be blurred out. So there's something to that we maybe have to do in aviation, but we are flying pretty high. And some of the data actually, in terms of security, comes mandated from the FAA, right? Because we're using at times, specifically at MIT Lincoln Laboratories, and I'm sure in your place as well, is we're using radar data where it could have national security concerns if someone got access to the specs of that data. So oftentimes that is a challenge for companies like Joby or Reliable Robotics that are trying to build non-cooperative sensors, and they say, can we have access to the radar data? The FAA says, no. That is national security data. I cannot give you an idea of what the coverage of our radar systems is. So that does come with its challenges.
Yeah.
And I think data security is obviously a really important and critical point for these AI systems, and I'm sure that all companies are taking it very seriously, and it's obviously evolving as we speak. I think part of some of these applications we can learn is from anonymized data, and really to make sure the processes are there and to glean and to use the strategies that we're implementing. For example, with the pilot training aspects, we can take the data anonymized and then show the benefits. The same potentially with ATC and obstacle avoidance, etc. You can show a lot through these applications without going into personal data and cybersecurity concerns, I think.
I mean, but don't forget, you're all wearing a tracker. Right?
Exactly.
You're carrying it all the time. You're taking pictures. There's AI in it already identifying your family members as you take pictures. So I think the public is becoming more and more aware about privacy violations, right? Yeah. How many letters do you get about your data got exploited by someone?
And it's still even beyond that. There is like a pretty public airspace as well. Keep in mind that anybody that has, a private jet, remember Elon Musk was kicking this guy off of Twitter because he created a Twitter account just to track Elon's private jet because we all have a tail number. And that tail number, all I have to do is go on flightradar24.com, right, or FlightAware, and I can track where Elon Musk is going or anybody else. So there's some data that actually is really open and accessible.
Yeah, we had one incident where we had a customer who flew with us and came back a second time and requested that we remove our registration number from FlightAware for the next round of tests because they thought that their competition could tell how well they were doing based on the FlightAware tracks.
Yeah, I mean, if you look at the UTM standard, right, you're not actually sharing your position data with your rivals. You're essentially giving them a 4D structure of where you're going to be, but within there, you're not actually telling them I'm exactly here, right? Only when there's conflict resolutions between those two crossing paths, then you can start sharing a little bit more if you want. But there is some privacy concerns here. Something that I've always thought about is a company that's trying to flood the market, why don't they just put a bunch of requests in a sector of a city, right? Just file them with UTM and control that sector. How do you respond to that? How do you know they actually flew those routes? So that's something that we're going to have to overcome in the future.
Okay. So going back a little bit into the AI in the cockpit and the perspective and the reaction that pilots may have with the idea of using AI in the cockpit, can you maybe comment on what reaction you're seeing from people who actually fly with this type of technology? And then which cockpit do you think will be the first to be equipped with AI in the future?
So we put pilots in the aircraft pretty often. And fixed-wing pilots, they're really surprised by how well our system works. Their response is that our systems do not resolve the traffic as well as the human eye, but it over and over again identifies the traffic before the human does. So it basically is a set of eyes that are always looking. And ultimately what a pilot wants is that if there is something there, just tell me to look up and what direction to look so that I can, check and see and make sure that I'm not going to fly into that hazard. Where we get just overwhelmingly huge response is, as you can imagine, because I've said it multiple times, is helicopter pilots, and particularly helicopter EMS, search and rescue, and on pilots that are flying aircraft that have no features. I'm talking about Robinson kind of helicopters that have no autopilot, no no IFR equipped. They're single engine systems. They are just absolutely blown away, and I'll never forget getting a search and rescue pilot into the airframe when we rolled out 2 months ago our wire detection application. And I mean, if anyone here who's a helicopter pilot, there's wire cutters at the top of the airframe and the bottom of the airframe. And if a helicopter pilot, if they ever fly into a wire, their best hope is that it gets caught by the wire cutter. If that does not happen, they are going back down plunging into their death. So it is an incredibly dangerous environment when they're doing rescues where there are power lines, where there are any kind of wires. And as I stated during my presentation, sometimes they knew that it was there, but the rescue, the mission, they have so much information coming at them. They're trying to engage with, if there is ground-based emergency, they have to engage with their hoist pilot, the hoist operator, their rescue operator. Somebody's down with the basket, right? There's so much going on that they can really just forget that I had that tail hazard and I don't see it anymore. And so that is one application where we took them up in the air, and when you're flying, I could not see the wires, and our system was picking up the wires.
And most AAM aircraft don't have wire cutters, right? So it's a big thing that we need for the future. Yeah, I think that, in terms of the feedback that we get from pilots when we show them about the adaptive learning and training, we again, like Yamaya said, we have a very positive response from pilots, and they're very progressive. They understand the benefits of these technologies, and they want to see this. There's obviously the challenge with reality and getting this, certified, regulated, etc. But pilots are usually excited about this as long as they can see the potential benefit for them, and as long as it's not like, okay, AI is replacing the pilot, AI is supporting me, how can it do that? And if they understand what it's doing, it's a real thing. I think one of the things about where we could see AI applications first is the AAM branch and towards Joby and those companies. There we have single pilot operations, which is very different from our commercial air transport. And so there is a need to provide the pilot with the additional information, like wires, like traffic, like navigation, particularly if the airspace becomes congested with UAS and other autonomous systems. So I really think there's a big opportunity that we see these technologies in AAM aircraft pretty soon.
Especially at the altitudes that we're talking about.
Exactly.
AAM vehicles flying, right? To your point, a lot of congestion down low, right?
Yeah, absolutely.
So to remain on the topic of augmenting pilots, especially in the context of emergencies, question from the audience is there any work being done to augment the pilot during an emergency, since emergencies can distract from critical flight operation? Second part of that question speaks more to general aviation, where we see a lot more accidents than we do with commercial aviation. And so follow-on question is, what about the augmentation in general aviation if the pilot becomes disabled in single pilot operations?
Yes.
Yeah, so take a look at what NASA did with the GCAS system, right, for the F-16s.
Yep.
That saved so many pilots when the pilot just blacked out because of the G-forces, right? So a system like that in general aviation would be phenomenal. I don't remember the name of the company, but there is a company that if the pilot, they just certified it, if the pilot becomes incapacitated, they would press an emergency button, right? Yeah, Garmin, it was Garmin.
It's the Garmin Autoland, emergency Autoland.
Yeah. So such a system is magnificent because in an emergency situation, it can take control and land the aircraft.
Yeah. And they can be implemented, I won't say before there's been a full kind of safety process, traditional long safety process. I won't quite say that, but think about if your safety case is, my system only needs to be better than a dead pilot. Mm-hmm. Right? That's a very different situation than implementing it where my system needs to be operable when I have single pilot operations and there's a pilot there. In this case, these are the passengers. If they lose pressure or something like that, or the pilot becomes incapacitated in any way, it's actually the passenger who pushes the button, and then it reroutes the aircraft to the closest airport. And it basically has, I believe it has like some kind of beacon that basically tells everybody, I'm landing blindly, get out of my way. Yep. So, in that same way, we could also implement our emergency landing system to go off runway. You can't do that kind of auto land system, does not work for helicopters. If I lose engine power in a helicopter, I have, say I'm flying a Robinson 22, I have 1.9 seconds to drop the collective and initiate an auto rotation. That's it. And I gotta know where I'm going real fast. Right? So we think our system would be great to use that. And there could be, again, if the system only needs to be better than sudden death, then you could perhaps take over the controls to drop the collective automatically and then already choose a target and initiate the auto rotation.
I think to add to your comment on the F-16, GCAS and trust.
Mm-hmm. Yes.
Early on, my understanding is there was pushback from the pilot community on having this system active in my jet. And that opinion, from what I understand, has come around 180 degrees.
Yeah, it changed real quick. Yes. As soon as pilots started getting saved by that system, it changed really quickly.
That's right.
Yeah.
And I want to build off of what Yamaya was saying because it was an important point in terms of like the time frame to actually make some of these decisions, because you could have a pilot that's not incapacitated, but because there is this back and forth that actually has to occur, assess the situation, work with air traffic control in terms of notifying of emergency situation, you might have already passed that critical time point such that you could have actually potentially navigated back to your origin or original airport, and then you end up in a worse scenario because you weren't able to act in time.
Yeah, this is why in collision avoidance, right, like TCAS auto-communicates between the aircraft and they find a resolution for both aircraft to avoid collision because they have 60 seconds before they're going to kill more than 500 people. So that's the timeline that you're working with.
Wow.
So we're jumping a little bit and going back to the topic of certification. And one question that is being asked is, how is AI information characterized by commercial certification authorities? And do you expect AI integration to increase the time required to certify systems for operational use?
Tough question.
Any comment on that?
I think if you go back to negotiating a certification basis for the aircraft, right? And then you've got to go and prove that you meet that certification basis. I think from my standpoint, what does that certification basis look like? And amongst all of us up here, I'm probably the least knowledgeable in that area, but sounds like the FAA is making progress and has put out a roadmap, so.
I think often another kind of comment that we get is people assume that 10 to the minus 9 or 10 to the minus 7 or 10 to the minus 5 is the requirement of the algorithm. But what do we actually certify? We certify an aircraft, an airframe, a propeller, an engine system, propeller system. We don't certify algorithms. So we start out with the CONOPS and we start out with an FHA that is, a aircraft-wide FHA, and then we break these down into subsystems, and each of these subsystems have an intended function. And what drives my design assurance level is going to be my intended function. And so we talked about traffic collision avoidance many times. I'm able to go and certify to a Dow Charlie because my intended function is just an alert. But if my intended function was to take exactly the same data and provide a resolution advisory, I got a higher design assurance level. If it were to take exactly the same data and provide an auto maneuver, I got an even higher design assurance level that I need to meet. And in each case, there is system-wide mitigations that occur. And so, for instance, I can say something like, well, my visual-based or my neural network-based system is only a backup to ADS-B, for instance. Well, I know ADS-B is always working, so I'm only going to turn on when I don't have ADS-B available to me, right? All of these are different ways that you can take exactly the same information, the same application of machine learning, but you have a different intended function and you come out to a much different level of rigor when you have to certify that system.
Yeah, but I think another part of that is that we need to train and have experts that understand how to certify these systems in the government part of the system, right? So the FAA, I think, is trying to bring in AI experts that know the technologies, know the algorithms, know how to test them. That's something that needs to happen. I mean, in the DoD, you have CDAO building tool sets so that their analysts, whenever they're giving, hey, there's a new black box that is going to work better than version 1, they have a test suite of tools that they can use to test that specific system. So I think to the part of the question about will it slow down the certification process, I don't think so. We actually will be in a transitionary period where we're going to have to train FAA individuals, train certification individuals how to think about AI, what are the boundaries of it, and what are the test cases that you need to cover.
I think, well, the EASA is way further along than FAA, though. Okay, the EASA published their first roadmap not long after we co-published with the EASA proposing the first guidance of what to do. So, you know, the EASA, they are now on their 2.0 roadmap. And, you know, they've been doing, the same folks that are driving this on the EASA side were the co-authors with us on the CODAM papers. They've been doing tours and telling people what to do and, you know, how to address this now for years. I think we published the first paper in like 2019 and then the second one in 2020 or 2021. And then from there, the EASA published their own paper, First Usable Guidance, and that was the 1.0. And so they are moving, funny enough, on their roadmap part, they're moving further. But, you know, we have to remind people that we're certifying with the FAA as well. And so there's this weird thing where we have the FAA folks that are the AI folks that are putting out roadmaps, but they have active people that are working on certifying, you know, programs. And sometimes I don't know if they're talking to each other or if at some point the folks that are working with us are going to slow us down because they're going to say, hey, the big AI folks say to stop until we figure out how we're going to do this. At this moment, the EASA has been really heads down. They really did a lot of study and they became experts in AI when they were working on this with us.
Thank you. So we have only a few minutes left, so I wanted to give you guys an opportunity to share your perspective as to what we can expect looking ahead. And so what do you believe will be the single most transformative AI innovation in aviation over the next decade? And what steps should the industry take now to prepare for and integrate this technology seamlessly?
Yeah, that's a difficult question, crystal ball question. I guess I would see the application of drones right now, UAS, that we see already today is going at a tremendous rate, and I do see the world in a decade from now where drones are running fully autonomous missions, and we have less and less human over those operations, really just monitoring to see how they're interacting and learning so much about how we conduct, particularly for defense applications. I will say that I do foresee the challenge with that we will have to start thinking about ethical decision making and how that's then into these AI algorithms, and that will become more and more prevalent as we go forward. So that's what I expect as in the next decade. I don't think we will see AI in the cockpit perhaps, but obviously we will have steps towards that. But really, that's the drone applications is massive.
I think there's a good amount of air transport that is experiencing the innovator's dilemma, whereby it is very difficult, it's very expensive and painful to implement new technology and innovation. And especially where that technology and innovation may or may not work or may not go bust. It's very expensive to build an aircraft. It's extremely expensive to run an assembly line and have a 20-year backlogs, right? And you don't want anything to be disrupting your assembly line. So leave that pesky new stuff over there because I need to get airplanes out as quickly as possible. And every single time you introduce new technology, it halts my assembly line and ultimately my revenue. But I believe that between AI-enhanced autonomy and in some cases electrification, general aviation has been kind of driving the disruption of this technology, and I believe that there are going to be some cases where they start stealing and eroding workloads that today are only resolved for air transport. And at that point, there's going to be incredible transformation of the industry.
I think with the push for advanced air mobility, there's a lot of technology being built for the autonomy, right? There's autonomy of air taxis, autonomy of UAVs. But we don't talk about a lot about the transition of some of that technology to our current commercial aviation, right? Current ATM. It's going to be fascinating to see how some of these systems cross that line and we become an even more efficient airspace where a common passenger will be able to benefit from that, right? I think it would be great if I could just walk through the TSA and have an AI system that just detects everything from me and I get on the aircraft. It would be great if we don't have revenue management systems that are targeting you because they know, hey, you're Olivia, you like to fly to this place a lot at this time, so I'm going to charge you a little bit more. That's the dangers where you have, but I'm looking forward to what aviation comes in the next 50 years.
Yeah, I think I'm definitely excited in terms of like all the smaller UAS technologies, UTM, advanced air mobility. I think the one part of advanced air mobility that may not get as much limelight, but I think is really important, and I'm excited to see the technology is actually in the wildfire space, right? I mean, wildfires are continually getting worse. I mean, there's record numbers of fires in terms of Colorado and California. So how we can actually use AI to increase situational awareness, team with first responders there, so that we can really assist in that space, which is just so critical in terms of human life at risk. So if we can advance that space, I think that's something I'm really excited about.
Yeah, from our perspective, I think it's setting up our flight test architecture to be able to support the things that we're talking about, to make it easy, make it efficient for folks to bring their autonomy on board and go test it, go validate it, go verify it, and ultimately push it along. From our perspective, if you look at the technology and readiness levels, right, they go from 1 to 9, right? 1, you're trying to change the laws of physics. 9, you're getting ready to go to production. Where we tend to find our sweet spot is in the middle, right? So, when we talk about crawl, walk, run, we're the guys that help walk. So, from our perspective, it's about making sure that we've got the test infrastructure set up to support what's coming next.
All right, we're at time. Wanted to thank you all for sharing your time, your expertise, and your insight. We hope to continue the discussion later today at the follow-on panel, but then wanted to give you all a round of applause. Thank you.